Dear all, welcome back. Let's proceed with the third problem of our second homework. Now we have solved two problems related to method of images, and in the next two problems we will be solving the Laplace equation for two different geometries and two different boundary conditions. One shell has to do with the rectangular coordination. You see we have a cube with length a and let's call this x, y, z. We have a cube and the upper and lower surfaces of cube state at the constant potential denoted by V. The other surfaces have the potential of 0. And given these circumstances, we need to find the potential at any point inside the cube. And then by using that potential distribution, we would like to find a surface charge density on the upper side of the cube. Okay, nice. What we will solve the following Laplacian equation in rectangular coordinates. It can be expressed in this form, and hopefully separation of variables method give us acceptable solutions for this type of a boundary condition. So I am just re-expressing the whole potential function independently from each other, and given these circumstances, this differential equation can be easily reduced to the following. You already have done this step a couple of times, so I'm just passing it through. Okay, you see the zeroth potential at the surfaces are valid for x and y coordinates. So in order to fit some sinusoidal into those dimensions, I am just making sure that these are equal to minus m square and minus n square. Or first of all, let me use m and n for integers, just for the moment. Minus alpha square minus beta square, which means that this is nothing but gamma square, which is equal to alpha square plus beta square. And if this is the case, xx can have two different solutions independently, and similar argument is valid for yy. However, in order to satisfy phi x0 yz is equal to 0, and then phi x equal to a phi yz is equal to 0, we can only work with the sine function, and furthermore we need to make sure that alpha is equal to m pi over a, where m is an integer not equal to 0, right? And second of all, the very same argument is valid for y equals to 0 xz and y equals to a xz, which give us the following. y can only be a function of sine beta y, where beta must be defined as np divided by a, where n is an integer different from 0. Okay. Hence, whatever the form of the z function up to now, by the way, of course, all of the orders of m and n except from the 0 are valid for this sort of boundary conditions could be satisfied. So I am just taking the integration of this amn, whatever zz is, but the rest goes as follows for the moment. M pi x divided by a, m pi y divided by a. Okay. But now we need to consider the boundary conditions we need to satisfy at upper and lower surfaces. Okay, that's the idea. That also we need to satisfy. And also remember that we have already wrote it down. Gamma square is equal to alpha square plus beta square, which means that gamma square is nothing but p over a square n plus n square. That's also another important point we need to remember. Okay. How shall we satisfy the boundary conditions for upper and lower surfaces? Now this is our purpose. Let's see what we need to do for the moment. Since phi xy z equals to 0 is v, phi x a is v, and second derivative of z divided by z is equal to gamma square, I am expecting to have general solution of the z as follows, right? Gamma z plus b minus gamma z. So exponential decay occurs, or any other form of exponential growth. In order to satisfy z0v and za v, in fact these are not directly equal to v, but for any order of m and n, they will be corresponding to some constant other than v and v. Of course, the v is the total potential. This is just a portion of it. We need to multiply it by some constant, so this is, let me denote it by v prime for the moment. In order to satisfy this, if you attempt to satisfy these two conditions, given the general form of the solution is in this form, the algebra is quite hard to finish. So instead of making this sort of an approach, we will be using the superposition principle, so that this cube of v and zeros will be the summation, that will be the superposition of 0v plus zero v. Okay, and I will call this side top and I will call this side down. Okay, so as you will see, it is much easier to satisfy this condition. The above part is V and the lower part 0. It is much easier to find the algebraic solution for this sort of a general solution. Hence, let me show it to you. For instance, at z equal to 0, we need to satisfy it to be equal to 0. So a plus b equals to 0, which means that b is nothing but minus a, which means that zz is in the general form of a gamma z minus gamma z, which can be re-expressed as, let me call this a prime, in fact it's 2a sine hyperbolic function of gamma z, zz. Okay, so let me also denote it by a prime. Very well. So now, given these, only one last boundary condition left in order to find the phi top. You see, I am now focusing on psi top up to now, but the boundary conditions for the vertical surfaces are not changed, which means that the analysis that we have done for x and y coordinates are still valid. So the general form of the solution for psi top xyz can be re-expressed in this form now: a mn multiplied by zz, which is sinh. Let me rewrite gamma in terms of mn, which is this one, pi over a m square plus n square z multiplied by sine m pi x a sine m pi y a. Okay, this is the general form of the solution for psi top. Are we done here? No, as I told you, we also need to satisfy psi x y z equals a is equal to b boundary condition. How can we do this, given that the general form of the solution is this? It simply means that I am now determining the coefficient of these orthogonal functions, right? So at z equals to a, I need to determine how I need to choose AMM, how I need to choose the components of these orthogonal bases such that I satisfy the boundary condition to be equal to v at z equal to a. Okay, that is the problem now. And for that problem, the problem is sort of an inverse Fourier problem, because we are analyzing the system and calculating the different compounds of the different harmonics. So for that purpose, we need to remember the orthogonality expansion, orthogonality equation for sine functions. In this case, from 0 to a, sine n px divided by a, sine n prime px divided by a dx is equal to a over 2 Dirac log n prime. Okay, as long as n prime are different, it means that this integration is equal to 0. If they are equal, this integration is equal to a over 2. How do I use that sort of an information? You will see it in a second. Okay. This is 3 and this is 4. use 4 to expand 3 in the dimensions of x and y. See, psi top x, y, z equals to a is equal to mn amn. My purpose is to figure out amn in order to make this solution unique. Since pi over a multiplied by a, which is giving me pi directly, m square n square sine mp x divided by a sine mpy divided by a. Let's take the integration of the both sides of the equation with respect to the harmonic of x first. Dx from 0 to a sine m prime px divided by a. Okay. And then let me take the integration over y-axis sine, let me call this m prime sine n prime py divided by a, and psi top xy z equals to a. So I need to take the integration for the other part too, which is now equal to what? Zero to a dx, 0 to a dy, right? mn amn since p this much, and then sine mpx a sine m prime p x a sine mp y divided by a and sine m prime pi y divided by a. Okay, so I have reached into the form that I would like to reach, because you see now I am free to use the orthogonality principle of these two guys in order to eliminate the whole summation, right? Because remember that I am taking the integration of x, which means that it is only non-zero in the case m equals to m prime. Otherwise it is equals to 0. Okay, and similar argument goes for the integration over y. Only n and n equals to n prime contributes to the overall summation. In that way we can figure out the corresponding component of the harmonic. Okay, that was the idea. So given these circumstances now, since let's check out the 4 again, this integration is equal to this much, a over 2 mn amn sigma mn prime, similarly sigma nn prime, but a over 2 again, multiplied by sinh argument. You see, this whole summation can be now summarized as a over 2 square sinh pi m prime square plus m prime square a m prime m prime. There is no summation anymore because these two canceled the whole summations over m and n and give us only a single term, which was the whole purpose. What is it equal to? It is equal to this summation, right? Let me take it from that side. Let me copy, paste over here. Sorry, let me bring it over there. Come on. Yeah. Again from 0 to A. Here. Nice. But what is it equal to? We know that it is equal to V now. So let me re-express my whole m prime and n prime. Let me just change this dummy variable to mn. Okay. That is nothing but equal to now 4 divided by a square sinh pi m square plus n square, right? Multiplied by this whole integration now. V multiplied by 0a dx sine mpxa 0a dy sine mpy divided by a. Okay, I could have taken the v outside because they are not dependent of x and y. It is always constant on those surfaces. So this integration turned out to be this one. And if you like, if we can go over, but I will not separate some time for this calculation. This integration is nothing but equal to a over m pi multiplied by 1 minus 1 to the power of n, and similarly this integral too. But in this case it is equal to m. Okay, but this is 0 for even n and 2 for odd n. Similar argument goes for the right side. Hence, overall, AMN is nothing but 2 comes from this side, 2 comes from this side. So the square of these giving me a 4 and multiplied by 4, 16v a square. Let me write it down clearly. 4v a square sinh pi m square n square multiplied by 2a m pi 2a m pi for m and odd. Okay, and a's shall cancel, which means that amn is nothing but 16v mn p square sinh pi m square n square. Now for a given m and n integers we can have our component. So in summation overall side top is equal to components of m and n from 1 to infinity amn on 16v mn p square sinh pi m square n square. Okay, and then sine mpx divided by a mpx divided by a mpy divided by a and sinh m square n square pi z divided by a. Okay, but remember this was the single component of it, but do not worry, we do not have to repeat all of it. because there exists, of course, a symmetry between the two. Psi top, or let me write bottom in terms of top. Psi bottom is symmetric once I flip it with respect to the a over 2, right? And xy xyz is equal to psi top xy a minus z. That's the whole idea, right? Hence, nothing will change except this one. Instead of z now, I need to place it as a minus z, which means that psi total, which was the whole purpose, xyz is equal to let me copy it from above. It will be let me delete it. I would like to just put the a minus z version of this. Okay, m pi y. Let me pass into drawing again. Yes, this is m, and now with this I need to add sinh m square n square a minus z pi divided by a. Plus. Nice. This is the, now not top but total potential. Let me repeat what I have done, because this sort of problem is quite important to understand. In fact, other geometries will just give us the different orthogonal bases and nothing more than that. I mean, instead of knowing the orthogonal expansions of the sine functions, we need to know the orthogonal expansion of the Legendre function for a spherical coordinate with azimuthal symmetry, for example. In this case, the Laplacian had been solved by taking the use of x and y coordinates are 0 at the surfaces. Those shall give us sine functions, but the problematic coordinate was the z coordinate. In that coordinate, in order to satisfy boundary conditions which are equal on top and bottom, since I have found the algebra harder to work with respect to the one that one of the surface is 0 and the other one is v, I have continued with the superposition principle, and I first solve phi top, given that the lower side is 0, the upper side is v. To satisfy that, z0 should be equal to 0, whatever the m and n are. So which means that b is equal to minus a, and they are giving us nothing but the sinh functions, hyperbolic sine function. Okay, and now the most general form up to now we have obtained is given in 3. Okay, but we are left with the satisfaction of upper coordinate, upper surface boundary condition. So in order to satisfy that, now I need to uniquely determine AMN, given that at z equals to a, it is equal to v. So now I am taking the integration to decompose the whole structure into its x and y harmonics. Okay, given that the orthogonality equation is this one for sine functions. Okay, so by putting some time on it, psi top is equal to this, and let me take the integral with respect to the dummy harmonics m prime and n prime. So I need to do the very same process on the right side. So the right side, if you be careful, now are given us the chance to take this AMN outside of the whole summation, due to the fact that m and m prime sign integrations can only be non-zero in the case m equals to m prime. And that is the whole idea over here. But while we are doing this process, we need to be careful because a over 2 constants are coming from the orthogonality condition. So now by taking these out, now I end up with am prime and n prime, but the left side of the integration still remain to be solved. But we do know that that is equal to v, and yeah, you see the rest of the integration is easier. At the end of the day, amn turned out to be this coefficient as a function of m and n. Now I can express top, but the purpose was not the calculation of top but the overall. But we do know that bottom can be expressed in terms of top in this form. So the total psi is this much. Okay, very nice. It's a typical problem of Laplacian for any sort of an exam in rectangular coordinate. Are we done yet? No. We need to also find the charge density, but we do know that the charge density is equal to E0 delta phi or delta psi total delta n. I evaluated it at surface. In this case, it is corresponding to delta psi total divided by delta z at z equal to a. Okay, so I need to take the derivative of this whole equation with respect to z. It is not a hard work to see that since alpha z integration with respect to z is alpha cos alpha z, which means that this can be expressed as E0 16v p square mn. I need to take x and y coordinates as still by y divided by a, but now I need to make sure that alphas are taken outside the coefficient of z's. In this case they are m square n square pi divided by a multiplied by, this is given me cos of the same argument minus, this is given me cos again the same argument. What is the same argument? mn square pi a minus z divided by a. Nice. This is the surface charge density. What is the sign here? Is it plus or minus? You see, this is V, right? I would like to know it for upper side. Sigma E0 delta psi over delta z But in order to find this sort of a curve, I need to take the integration with respect to the minus z, and the minus sign again must be multiplied by minus, which means that is plus. So this is plus over here. Nice. Okay. This is the end of the solution of the third problem. Let me proceed to the fourth problem now. Okay, this is the fourth problem, again a Laplace equation problem, but in this case we have a spherical symmetry. We have a spherical geometry with an azimuthal symmetry. What is meant by azimuthal? It means that the whole geometry is independent of phi. It's all symmetric along the rotations over the angle of phi. So I cannot see any physical process that changes, physical quantity that changes as we rotate it along the phi axis. We will be solving the Laplace equation for the spherical geometry. Again, phi shall be equal to 0 under the conditions that psi r equals to r, theta smaller than theta 0 is equal to v, psi r equals to r, theta greater than pi minus theta 0 is equal to minus v, and then psi r equals to r, theta lower than this, greater than this, is equal to 0. These are the conditions we need to satisfy. The most general form of the solution for a spherical coordinate, for a spherical geometry with azimuthal symmetry is this one. You have already derived this. I am not doing it again. You will be remembering it in a second. AL to the power of R to the power of L, BL divided by R to the power of L plus 1, PL cosine theta. Also remember that inside, psi inside, as R goes to 0, I expect to see some finite number. Okay. As in order to satisfy it now, as R inside, as R goes to 0, it should be going to finite number if BL is 0 for all else. Before solving in the details, I would like to motivate you with the purpose of the question here. We would like to find the angle theta 0 such that the electric field inside the shell will be as nearly constant as possible near the center. Okay, so we would like to find such a change of potential function that its derivation around the origin is almost given as a constant. It shouldn't be dependent upon much on r, okay, or much on theta. That is the idea. So once we are close to the solution of this sort of geometry with these given boundary conditions, we need to modify. We need to choose the coefficient such that the potentials derivation, the gradient of the potential is nearly constant on the neighborhood of origin. Okay, that's the idea. So if BL is constant, psi r theta is now in the form of the following: L from L0 to infinity AL R to L PL cosine theta. Okay. Now again, problem needs an orthogonal expansion now, but in this case we need to expand the whole argument over the PLs. So we need to remember the orthogonality relation for Legendre polynomials. And that relation turns out to be 0 to pi theta sine theta Pn cosine theta Pm n prime cosine theta is equal to 2 over 2m plus 1 and n prime. Okay, we will be using this. In order to satisfy the boundary conditions at the surface of the sphere, which means that r equals to, what was it, capital R? Yes, capital R. I am doing the following: psi r theta is equals to L0 AL. Let me define it as let me change it like this: R over R to the power of L. I did nothing but adding this R to the power of L into this. Instead of make the things simpler here, I am just dividing it with the capital R, so that at R equals to capital R it turns out to be 1, and then PL cosine theta. We have done similar thing on the previous recitation too. I am just replicating to make sure that once I am studying the boundary condition at R equals to capital R, it is easier to work with. I am not carrying the R to the power of L each step by step on an algebraic process into AL. I am not doing it. Instead of doing that, I am just scaling my R. Nice. If this is the case, let me take the integration again with the very same idea with the previous problem, but for this one, for Legendre polynomials: sine theta P L prime cosine theta psi r theta, which is equal to 0 to pi d theta sine theta L0 AL PL cosine theta PL prime cosine theta. Okay, but you see, now again this whole expression turns out to be nothing but 2 divided by 2L plus LL prime over the L and AL, right? This was the whole process, which means that AL prime 2 divided by 2L prime plus 1 is equal to this one, 0 to 2 pi d theta sine theta PL prime cosine theta psi r equals r theta, which means that AL is nothing but 2L plus 1 divided by 2, 0 to 2 pi d theta sine theta PL. I have changed from L prime to L, cosine theta psi r and theta. This potential, remember, something like this, right? Over there and over there, plus V, minus V, and 0. Okay, now I have found my ALs. I am not done yet, because I didn't satisfy this condition. I need to take the whole integration. This can be valid for any sort of a potential distribution. So I would like to notice a couple of things before doing that. To proceed, let's remember what those Legendre polynomials look like, right? For instance, for the zeroth order, P0x is equal to 1. P1x equals to x. P2x equals to 1 over 2 3x squared minus 1. For 3x 1 over 2 this much, one over 8 this much. Okay, you see from this shape you can see that theta must be the minus sign of r equals to r pi minus theta, right? But cosine theta is minus cosine pi minus theta. Why I am doing this? Because the Legendre polynomial has the argument of cosine theta, and you see this one is an even function, this one is an odd function, even function, even odd, and even, and it goes on like this. However, in order to satisfy my boundary condition, right, for plus v and minus v, I can only choose the odd powers of the Legendre polynomials. Otherwise, I cannot obtain this antisymmetry. Why? Because you see PL theta over here, I will be taking the whole integration, but for the upper side I need to obtain the plus sign, for the lower side I need to obtain the minus sign. In order to satisfy this, once I change the argument of cosine theta, I need to see a change in the sign of the Legendre polynomial, and that is only possible for the odd powers. Okay, in order to satisfy this, even else must be 0. Okay, only odd powers may contribute. That was one of our concerns for the moment. Are we done? No, because let's re-express the whole potential function. It was this one, right? Psi r theta L from 1 now to infinity, L odd AL r over r to the power of L PL cosine theta. Okay, I can calculate what the ALs are by using this, and given that psi r equal to r in this form. However, my purpose is to achieve something, right? Achieve something given these boundary conditions. What is that purpose? That purpose, I need to obtain E field, which is nothing but this guy, near the origin, such that it is nearly constant. You see, for the first order, A1 r over r P1 cosine theta plus A3 r over r cube P3 cosine theta plus A5 r over r5 P5 cosine theta. Nice. Once you take the integration of this with respect to the r, for instance, and the other components, you see the order of r will be simply taken decreased. So E field will be proportional to A1 over r P1 cosine theta plus A3 r square r cube P3 cosine theta, and it goes on like this. And the fifth order, r over 4 r5 P5 cosine theta. My purpose is to achieve the E field distribution such that the variation along the r-axis is minimum. This is a constant of r. However, this term is not, and I can achieve my purpose by simply assigning that A3 is equal to 0 for theta equals to theta 0. Okay, so that E field around the origin is constant as possible, is constant as much as possible. Of course, it is not constant overall, but that is the best we can do, given that the E field is an expansion of P1, P3, P5, etc. If I can equate A3 to be 0, yes, someone claim that A5 and A7 will keep contributing, but their contribution is much lesser with respect to the first and third orders. First order is nearly a constant of r, and hence the best design can be achieved through A3 to be equal to 0. That's the idea. But we have already calculated what the AL was. So A3 is nothing but 2L plus 1 divided by 2, which is 7 divided by 2, 0 to pi d theta sine theta, P3 cosine theta, and psi RR theta. It needs to be equal to 0. Okay, this is, I have already write it down, 1 over 2, 5 cosine cube theta minus 3 cosine theta. Hence 0 to pi d theta sine theta, theta 3 cosine theta, psi theta is equal to 0. I just dropped off the coefficients. Okay, let's remember the geometry again. Theta 0, v minus v, which means that it is plus v from 0 to, what was the definition of theta 0? Let me check it again. Yeah, I have wrote it down wrongly. Let me correct it. Theta 0, 0 to theta 0, it is plus 1, right? D theta sine theta, phi cosine cube theta 3 cosine theta. It is 0 inside in that interval, minus v from pi theta 0 to pi d theta sine theta, phi cosine cube theta 3 cosine theta again. It must be equal to 0, this whole expression, so that we can find what the theta 0 that makes the A3 0. And if you do this by cosine theta equals to u minus sine theta d theta shall be equal to du, at the end you end up with the following: 1 to cosine theta 0 minus du u cubed 3u minus cosine pi minus theta 0 to cosine pi minus du u cubed 3u must be equal to 0, which at the end give us the followings. Let me see it. Let me write it down as cosine theta 0. So 1 over 4 plus over 4 minus 3x squared divided by 2. Okay, and that is given us this much, this equation. Hence x is equal to 1 over 5. This is cosine theta 0, which means that theta 0 63 degree is the one that makes A3 0. Hence the E field a constant. E field constant as much as possible. Near the origin. Okay. That was the purpose of the question. You see, we have done the very same logic with the previous example, but here, since our coordinates along theta and the boundary conditions do vary along theta, we need to figure out the components of the Legendre polynomials. While we are doing that, we have been smarter than usual, so that we have already eliminated the even orders. You will be already seeing it once you do the whole boundary condition satisfaction so that the only odd terms will remain. But our purpose was not to find the general solution, but to design theta 0 such that the E field is constant along the, almost constant, as possible as constant. But the most variation comes from the third order due to the E field equation of this form. So I would like to make sure that the third order is just equals to 0, and that can be done through this process. We already know what AL is equal to, as the A3 is equal to this one, so the rest is just a careful algebra. And at the end, the theta 0 is equal to 63 degree is given us what we want. Thanks for your listening. I will be continuing with the rest of the problems on the next hour.